Good morning to all my dear students. How are you? I hope you all are fine, fit, and healthy. Take care of yourself, keep studying, stay protected, and stay safe from coronavirus. And obviously, enjoy learning at home. With this, I, Ms. Rupali Avare, welcome you all for this today's session on chapter Motion. This is the part third and last part of this chapter. Already in the earlier parts 1 and 2, we have learned many concepts related to this chapter. Today, at the end of this session, you will be able to understand the concepts of equations of motion by graphical method, uniform circular motion, and we'll see some numericals related to this. Now, you might be thinking that why to study these equations of motion by graphical method? What is the importance of graphs? So, already we know that graphs provide a convenient method to present basic information about a variety of events. For example, in the telecast of a one day cricket match, vertical bar graphs show the run rate of a team in each over. As well as you have studied in mathematics, a straight line graph helps in solving a linear equation having two variables. Similarly, we can use the graphs to describe the motion of an object. With this, modern day ideas are encoded in a compact way by using the mathematical notations. Equations contain the information which is equivalent of several sentences. Similarly, Newton studied the motion of an object and he set equations to relate the parameters involved in the motion. These parameters are displacement, velocity, acceleration, and time. But even though equations are great for describing situations, but sometimes one needs a picture to get a better understanding. And hence, a mathematical picture called graph is the best way to convey the events in a compact form for better understanding. So, let us derive these equations of motion by using graphical method. Newton gave three sets of equations like v is equal to u plus at, v square is equal to u square plus 2as, s is equal to ut plus 1 half at square, where u stands for initial velocity of the object, a stands for the acceleration of the object, t stands for the time, v stands for the final velocity of the object, and s stands for the distance traveled by the object. Now, let us see how to derive these equations by using the graphical method. Before that, let us understand this graph. The graph shows the relation between speed and time, where an object is moving with uniform acceleration. Uniform acceleration means the velocity is increasing at a constant rate. As we know that speed is a function of time, we have taken speed on the y-axis and time on the x-axis. If you will observe the graph, at time t is equal to O, that is t is equal to 0, the speed is also 0. But as time passes, when object reaches time is equal to q, the speed of an object is equal to r. If you will take slope of this graph, you will get the acceleration at any point. Now, we are going to use the graph of velocity time to derive these equations of motion. So let us start to derive the first equation of motion, that is also known as the equation for velocity-time relation. For that, consider the velocity-time graph of an object moves under uniform acceleration as shown here. But now with u is not equal to 0. In the earlier graph, u was equal to 0, but in this graph, u is not equal to 0. From this graph, we can see that initial velocity of the object is u at point D, and then it increases to v when it reaches point B. In time t, the velocity changes at a uniform rate a. With this, we have drawn a line parallel to x-axis dA from point D, from where the object starts moving, as well as we have drawn another line BA from point B parallel to y-axis, which meets at E, the x-axis. From this graph, we can say that OA is equal to time, as well as we can say BE is equal to AB plus AE. See, this BE is the sum of BA and AE. Now, here we can say that BE is equal to V. We can replace AB is equal to DC and AE by OD. So, substitute these values in this equation, will get V is equal to DC plus U. Now, as we know that the object is moving with uniform acceleration, so we know that acceleration is nothing but the change in velocity upon time taken. Here, we can find the change in velocity by final velocity minus the initial velocity. Therefore, A is equal to V minus U upon T. As V is equal to OC and U is OD, so if you will subtract OC minus OD, you will get DC. So, A acceleration is equal to DC upon T. Just cross multiplying, we are getting AT is equal to DC. Now, we'll substitute this value in equation 1. We'll get V is equal to AT plus U. Just rearrange this equation, we'll get V is equal to U plus AT. So this equation is giving the relation between the velocity, acceleration and time, and this is known as the first equation of motion. Now, by using the same graph, let us derive the second equation of motion. The second equation of motion is giving the relation between the position and time. Now, again, let us consider that the object has traveled a distance s in time t under uniform acceleration a. The distance traveled by the object is obtained by the area enclosed within this trapezium A, B, D, O, E. Let in the time t, the distance covered by the moving object is S. The area of trapezium A, B, D, O, E is equal to it is the sum of area of triangle and the sum of the rectangle. If you will see the graph, you will note this complete area is the sum of this triangle plus sum of this rectangle. So we can say distance is equal to area of triangle ABD plus area of rectangle ADOE. Now just use the formulas for areas and we'll get S is equal to 1 half into AB into AD plus OD into OE. Now as we know that AB is equal to DC and OD is initial velocity and OA is the time. So just substitute the values, we'll get S is equal to 1 half into DC into AD plus U into T. Now we can also write this as S is equal to 1 half AT into T plus U into T is UT. Here we have substituted the value of DC is equal to AT. For that you can refer equation 1. And we know that AD is T. So we can write S is equal to 1 half AT into T plus UT. Now just multiply and you will get S is equal to 1 half AT square plus UT. Rearrange this equation, you will get S is equal to UT plus 1 half AT square. This equation is giving the relation between the displacement and the velocity. This is known as the second equation of motion. We can use this expression to find out the distance covered by an object which is moving with uniform acceleration. Now let us start to derive the third equation of motion. Again we are going to use the same graph because the object is moving with the uniform acceleration. This equation is giving the relationship between position and velocity. So here the distance covered by the object moving with uniform acceleration is given by the area of trapezium ABDO, and the area of trapezium, that is equal to 1 half into sum of the parallel sides plus distance between the parallel sides. So we can write the distance covered by that object is equal to the area of that trapezium, which is equal to 1 half DO plus BE into OE. So we can write S is equal to 1 half U plus V into T. And as we know that from equation 2, acceleration is equal to final velocity minus initial velocity and time. Just rearrange this formula, you will get T is equal to V minus U upon A. Substitute this equation 4 in equation 3, you will get S is equal to 1 half U plus V into V minus U upon A. Then just do cross multiplication, do the calculations, you will get V square is equal to U square plus 2AS. This equation is giving the relation between the position and velocity, and this is known as the third equation of motion. Now I hope that you all have understood how to derive these equations by using the graphical method. Now let us solve some of the numericals related to these three equations. A train starting from rest attains the velocity of 72 km per hour in 5 minutes. Assume that the acceleration is uniform. Find the acceleration and the distance traveled by the train for attaining this velocity. Now, whenever you solve any type of numerical, first step is to write the given quantities. And if you don't understand this example, just read it twice and thrice. You will get a clear idea about it. And then go to the solution. Okay. So in this solution, what is given? It is stated that the train starts from rest. If a train is at rest, that means it is not having any velocity. That means its initial velocity is 0. And then it attains the velocity of 72 km per hour. That means the final velocity is 72 km per hour. Here we have just converted into meter per second. And the time for this is 5 minutes. So the time is converted into the seconds. And it is stated that the train is moving with uniform acceleration. Uniform acceleration means the velocity is increasing at a constant rate. And first we need to find out what is the acceleration. Now here, as we know the final velocity, initial velocity and time, we can find out acceleration as final velocity minus initial velocity upon time, which is equal to 20 meter per second minus 0 meter per second divided by 300 seconds. You will get the acceleration is equal to 1 upon 15th meter per second square. So we know now the acceleration, and we want to find out what is the distance traveled by the train for attaining this velocity. Now for this, which equations we can use? So we have two equations, Newton's second and the third equation of motion. Now which equation we can use? So we are going to use the third equation of motion, that is giving the relation between position and velocity. As we know the acceleration, we know the final velocity, initial velocity, we can calculate the distance traveled. So we can use 2as is equal to v square minus u square, and as u is 0, so on rearranging this equation we'll get s is equal to v square upon 2a. Just substitute the values, we'll get the distance traveled by the train is equal to 3 kilometers. Is that clear? Now let us move towards the another example. Let's see the example. A car accelerates uniformly from 18 km per hour to 36 km per hour in 5 seconds. Calculate the acceleration and the distance covered by the car in that time. So first step is write whatever are the given quantities. Again, it is mentioned that a car accelerates uniformly. That means it is a uniform acceleration, right? Velocity is increasing at a constant rate. Here, a car is having certain initial velocity. The initial velocity is not is equal to 0 because the car is not at rest. And that initial velocity is 18 km per hour converted into meter per second. And the final velocity is given, that is 36 km per hour, again converted into meter per second. And The time is given 5 seconds. First, we asked to find out what is the acceleration. So just use the formula of acceleration is equal to final velocity minus initial velocity upon time. So on substituting the values and calculating the values, you will get the answer as 1 meter per second square. That means the acceleration of the car is 1 meter per second square. And second, we want to find out what is the distance covered by the car in time t. So we can use the formula s is equal to ut plus 1 half at square. Substitute the values u, t, acceleration and again time. You will get the distance traveled by the car as 37.5 meter. So in this way we have find out the acceleration and the distance covered. Here to find out the acceleration, we have used Newton's first equation of motion, and to find out the distance we have used the Newton's second equation of motion. But to find out the distance we can also use the Newton's third equation of motion. Now let us understand it with another example. The brakes applied to a car produce an acceleration of 6 meter per second square in the opposite direction to the motion. If the car takes 2 seconds to stop after the application of brakes, calculate the distance it travels during this time. So if you will read this example carefully, the brakes are applied to produce an acceleration of 6 meter per second in the opposite direction to the motion. That means it is a negative acceleration. Therefore, A is equal to minus 6 meter per second square. And the car takes 2 seconds to stop after the application of the brakes. So T is 2 seconds. So after 2 seconds the car is going to stop. That means its final velocity is going to be 0. And find out the distance traveled during this time. So we want to find out what is S. But for that, we need to know what is the initial velocity. Because once the brakes are applied, the car is going to stop. That means its velocity is going to equal to 0. That means a body is having certain initial velocity, but final velocity is 0. So we can find out this initial velocity by the first equation of motion. V is equal to u plus at, where V is 0, u we want to find, and acceleration is minus 6 and time is 2 seconds. Just on substituting the values, we'll get its initial velocity as 12 meter per second. Now we got the initial velocity, we know the final velocity, we know the acceleration, we know the time, we can find out the distance. So use the equation which gives the relationship between the initial velocity, time, acceleration and the distance. So S is equal to ut plus 1 half at square. Just substitute the values, you will get the distance traveled by the car is equal to 12 meters. This is how we can use these Newton's equations of motion to find out the numericals. Now let us start with the uniform circular motion. But before that, let us understand what is meant by circular motion. A circular motion is a movement of an object along the circumference of a circle or rotating along a circular path. For example, artificial satellite orbiting the Earth, right? A ceiling fan blades rotating around a hub. A stone which is tied to a rope and is being swung in circles. A car turning through a curve in the racetrack, etc. So these are some of the examples where you will observe the objects are moving along the circumference of a circle, or the path which is traversed by them is circular. So such type of motion is known as circular motion. Now, the circular motion, it can be of two types: uniform circular motion or non-uniform circular motion. As we know, uniform circular motion, when the object is moving at a constant angular rate of rotation and when the speed is constant, then such motion is known as uniform circular motion. Whereas in non-uniform circular motion, the rate of rotation is changing. It is not uniform. The rotation around a fixed axis of a three-dimensional body involves circular motion of its parts. Since the object's velocity, as we know that velocity is a vector quantity, so as the object's velocity is a vector and it is constantly changing the direction, the moving object is undergoing acceleration by a centripetal force in the direction of the center of rotation. Without this acceleration, the object would move in a straight line according to the Newton's law of motion. See, though the body is having a constant speed, but we know that its velocity is not constant. Why the velocity is not constant? Because the speed is a scalar quantity. It doesn't depend on the direction. It only depends on the magnitude. Whereas velocity, it cannot be constant because the object is continuously changing its direction. Right? Hence, the velocity, it can't be constant. As well as the object is moving continuously in a circular path. That object is moving in a circular path, that is because of the acceleration and the velocity, which keeps that object moving in a circular path because acceleration and velocity both are perpendicular to each other. So let us understand in detailed uniform circular motion. Now, when the velocity of an object changes, we say that the object is accelerating. The change in the velocity could be due to the change in its magnitude or due to change in its direction of motion or both. Now, we'll understand the uniform circular motion through one example. Before that, tell me, can you think of an example when an object does not change its magnitude of velocity but only its direction of motion. For that, let us consider an example of the motion of a body which is moving along a closed path. Let's consider an object is moving along a rectangular track A, D, C, E. Let us assume that the athlete runs at a uniform speed on a straight paths like A, D, D, C, D, E and E, A. In order to keep himself on the track, he quickly changes his speed at the corners. Tell me, how many times will the athlete have to change his direction of motion while he completes one round? Obviously, it is clear that to move in a rectangular track once, he has to change his direction of motion 4 times. Correct? Now consider, instead of rectangular track, the athlete is running along a hexagonal shaped path A, B, C, D, E, F as shown here. In this situation, the athlete will have to change his direction 6 times while he completes one round. What if the track was not a hexagon but a regular octagon? So, with this, athlete he needs to change his direction 8 times, right? Now, what would happen to the shape of the track as we go on increasing the number of sides indefinitely? If you do this, you will notice that the shape of the track approaches the shape of the circle and the length of each of the side will decreases to a point. If the athlete moves with a velocity of constant magnitude, his velocity is due to only change in the direction of motion. And the motion of the athlete moving along a circular path is therefore an example of an accelerated motion. Right? So we can say that when an object moves in a circular path with uniform speed, its motion is known as uniform circular motion. Now, how to calculate the distance and speed in case of the circular motion? So we know that the circumference of a circle of radius r, it can be given by 2 pi r. If the athlete takes t seconds to go once round the circle path of radius r, the speed v is given by distance upon time. And here the distance which is traveled by an object is equal to the circumference of the circle, which is equal to 2 pi r upon t. Clear? So this way we can find out the distance and the speed of an object in case of the circular motion. Now, what is the direction of acceleration and velocity in circular motion? For that, consider an example. Take a piece of a thread and tie a small piece of stone at one of its end. Move the stone to describe a circular path with constant speed by holding the thread at the other end. Now, let the stone go by releasing the thread. Can you tell the direction in which the stone moves after it is released? By repeating the activity for a few times and releasing the stone at different positions of the circular path. Check whether the direction in which the stone moves remains the same or not. Do this activity at home. Observe it carefully and note down your observation. You will observe that on being released, the stone moves along a straight line which is tangential to the circular path. This is because once the stone is released, it continues to move along the direction it has been moving at that instant. This shows that the direction of motion changed at every point when the stone was moving along a circular path. So from this, it is clear that though the speed is constant, the directions are continuously changing. So we can find out what is the direction of acceleration and the velocity in circular motion also. So always remember that in circular motion, acceleration is always towards the center and the velocity is always along the tangent as shown in this figure. So we can see the direction of velocity and acceleration at different points in the circular path. Is that clear? In day-to-day life, you see many examples where you will observe the uniform circular motion. So as a homework, just write down the examples of an object which are moving under the uniform circular motion. With this, we'll stop for this today's session. Thank you and take care of yourself. Go and wash your hands for 20 seconds. Stay fit, stay healthy and stay protected from coronavirus. Thank you.